Hi everyone, in this video we are going to look at a power series and try to figure out for what values does it converge. Okay, so for this example I'm using a series from 1 to infinity of -1 to the n minus 1 power times x to the n over n. Okay, so remember power series, you have powers of x as part of your series. So let's just look at a couple of terms first to see what this series kind of looks like. So when n is 1, this -1 becomes a -1 to the 0, which is +1. Okay? Plugging in a 1 here, this is x to the 1 over 1. The next term, when I plug in 2, I'm going to get a +1 for my powers, so, or exponent here, so that's going to be -1. And then this is going to be x squared over 2. Let's just do one more. When I plug in 3, this is going to be -1 squared, which is +1, x to the 3 over 3. And make this look a little better, x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, and so on. Okay, so that's what this series would look like. Notice it's actually alternating series. So how do we figure out how this converges? Okay, so let's use the ratio test. Okay, so remembering a little bit about the ratio test, let me just remind you really quick. For the ratio test, you wanted to compute this ratio specifically. Let me add test into here, ratio test. The ratio that you want to look at is a sub n plus 1 over a sub n, but the absolute value, okay? Just meaning the nth term, then and the nth plus 1 term. And you take this limit as n approaches infinity. And then depending on the outcome, you have different cases where this converges, diverges, or this test is inconclusive. So for us, I'm just going to change the notation. I'm going to use u sub n, so u sub n plus 1 and u sub n, because we are dealing with an alternating series here, and the u sub n is reserved for like after the minus sign, so basically this part right here. Okay, and so let's just separate these two things so we can kind of use some algebra in just a minute. So u sub n is just going to be x to the n over n. Okay, now I do need to be careful. I am going to take the absolute value, so let me go ahead and throw that on there now. And n starts at 1, so what I really have to just guarantee is that x stays positive. So I'm going to put my absolute value on the x. Alright, so for u sub n plus 1, I get, everywhere I put an n, put an n plus 1. Okay, so x to the n plus 1 over n plus 1. And again, anywhere with an n, we're starting at +1, so you don't really need the absolute value bars on that part. We have absolute value x to the n plus 1. Okay, now what we're going to do is basically just some algebra to simplify this ratio when we divide, and then we'll see what we can do with our limit from there. So let me just clear this out a little bit. Don't really need to write this series expanded right now. So we are going to divide u sub n plus 1 over u sub n, absolute value. So that looks like, and I'll just write it in a few steps, x to the n plus 1 over n plus 1 divided by, so that's the u sub n plus 1, divided by x to the n, absolute value, over n. And you can skip this step if you know that the very next step is to flip and multiply, because you do have a fraction divided by a fraction. So you can just jump right here and you could say absolute value x to the n plus 1 over n plus 1 times the reciprocal of the u sub n term. So n over absolute value n to the n power, x to the n power, excuse me. Okay, now here's a little bit algebra for us other than what we did so far. We have this x to the n plus 1 power. Using our exponent rules, just a little bit of side work here. X to the n plus 1 is the same thing as x to the n times x to the 1, which is just x to the n times x, because our rules about rules of exponents from algebra. So I can rewrite this expression as absolute value x to the n times absolute value of x over n plus 1. I'm going to go ahead and group that. And then over here, still n on top, absolute value x to the n on bottom. And then we get to simplify. Yay. So let's divide out x to the n, top and bottom. And so this is what we're going to take the limit of. So let me clean this up a little bit and we'll put it right here. Okay, so we are going to take the limit according to our ratio test as n goes to infinity of, let me go ahead and take this n and kind of scoot it over on top of n plus 1, n plus 1, and then it's times absolute value x. So I'm just taking everything we didn't cross out from over here, just rearranged it slightly. Now I'm going for n approaching infinity, so I'm going to go ahead and just divide all the terms here in this expression by the highest power of n from the denominator. So let me squeeze this in here a little bit better. Divide by n, and we simplify that, and the limit as n goes to infinity, this is going to be 1 over 1 plus 1 over n. Get rid of my side work here. Times absolute value of x. This is going to be, as n approaches infinity, 1 over 1 plus 0 times absolute value of x, which is absolute value of x. Okay. Now, what does that tell us? We did all the algebra side of it. Okay, we simplified this limit, we applied our ratio test, but now based on the conclusion of the ratio test, we have to say something about this answer and how it tells us about the series convergence. Okay, so let me remind you of the 3 outcomes for the ratio test. Okay, so our ratio test said that if we take this limit of this ratio of the nth plus 1 term over the nth term, absolute value, and whatever it equals, in our case we're just using the Greek letter rho to signify what this limit equals. Depending on what rho equals, we have 3 possibilities. If this limit equals something less than 1, it's absolutely convergent, this series. If this limit value was greater than 1, divergent. Okay, our series diverges. And if it just so happened to equal 1, then this test is actually inconclusive. So we didn't get a number out of our limit, we got absolute value of x. So now depending on what absolute value of x equals, we're going to get different possibilities for this series. And so let's just kind of work with what I have written here. We have that our limit outcome was absolute value of x, so we can say, let's just erase this, that absolute value of x, when it's less than 1, this series converges absolutely. When absolute value of x is greater than 1, well, this series diverges. Okay? And then when absolute value of x equals 1, this test doesn't tell us enough information. And so what we're going to do is, this is good, but we need to explore this last part. So notice the 2 possibilities here. Absolute value of x is 1 when x is 1 or x is negative 1. And so we have to look at both of those 2 separate cases on their own to make some kind of conclusion. So let's explore when x is 1. So go back to our series here and plug in x is 1 and see what that looks like. So when x is 1, our series that we were starting with turns into this series. We just substituted x to be 1. And if you simplify, 1 to any power is still 1. This should look familiar, hopefully. This is just your alternating harmonic series. So this we've seen before. This is the alternating harmonic series. Okay? And if you recall, not sequence, sorry, series, if you recall what we learned about that, we learned that by the alternating series test, okay, the alternating series test, this converges. Okay, the series converges. Okay, so now we know that our series, when x is 1, can be added to the convergence part of our answer. Okay, so this converges. So then, do this one more time, and this time explore what happens when x is -1. So let's change this. So our last thing to check, when x was -1, we plug that in here, and then just a little bit of rules of exponents here. I can add my exponents because the bases -1 are the same. So I get 2n minus 1 as my exponent. And now you can kind of explore this if you need to by expanding it, but this is always going to be negative. Okay, 2 reasons why. One is by rules of numbers. Anytime you have 2n plus or minus like 1, like this, it's odd. It's going to always be odd. Okay, no matter what n is, you can plug in any n you want. This is odd, and -1 to the odd power is negative every time. The other way to see this is to just start putting some terms out, and let me show you that way if that makes more sense. Let's just pick a few. When n is 1, this becomes 2 minus 1. That becomes a 1 power. So that's -1 times 1 over 1. My next term, when n is 2, this becomes 4 minus 1. That's the 3rd power. So that's -1. Then that's 1 over 2. Let's do one more. When n is 3, this becomes 6 minus 1. That's the 5th power, which is negative. Okay, 1 over 3. And so we get -1 minus a half minus a third, and so on. All of the terms here would be negative. So what we really have going on here, this is just our harmonic series, but negative. So this is negative of the harmonic series. Okay, not the alternating harmonic series that we just saw, the original harmonic series. And if you recall, when we learned about the harmonic series, we learned that it diverges. Okay, so this, let me write it over here, diverges. Our harmonic series diverges, and if you want to look back as to why, it was because it's a p series. Okay, where p is actually specifically 1 in this case. So our series diverges when x equals exactly -1. So what does all of this mean? It means that for certain x values, our series converges, and for other x values, it diverges. So what's new for power series is that we have what's called a interval of convergence. On some numbers, the series converges, and on other numbers, it does not. Okay. So for us, if we put all this together, I'm going to show you visually what this looks like. Okay, so based on the results from our example, this power series converges for values from -1 to 1, but not including -1, and it diverges everywhere else. Okay, so that's just summarizing all of the outcomes we just talked about. So what does that look like? Okay, here's what it looks like. So our series, written here, expanded for the first few terms. If you notice, only between -1 and 1 on our x-axis do the graphs of our infinite polynomial, the graph of our series, converge to something. In this case, they're all kind of lining up right here in the middle. Now, if you look outside of this window, so this interval, okay, if you look to the left of -1, all the graphs start to like spread out. If you look to the right of +1, same kind of thing happens. The graphs all do something a little different. The green one starts to go down, the red one goes up, the blue one kind of shoots out sideways, and so on. But in between -1 and 1, all of these graphs are all acting very similarly. And so this is for different values of x. And so for values of x between -1 and 1, you get this similar behavior. Anything outside of -1 and 1, that's where it diverges. And so notice we don't include -1, but we do include 1 from how we tested just a minute ago. Okay, so that was for that example. Let's kind of summarize what's going on now with these convergent power series. So the convergence theorem for power series says the following. If the power series, notice what this one is, it doesn't have a center other than 0, and I'll explain the difference in just a moment, if this power series converges, so if we know it converges at some number, we're going to call that number c, then it converges absolutely. Okay, for all the x values less than the absolute value of c. So basically that means like between negative c and positive c for all those x values. For us, that was negative 1 and 1. Now, if the series diverges at some values, so at like x equals d, then it diverges for all values greater than absolute value of d. So what that would look like is all values bigger than the number d, and then this also represents numbers less than negative d. So for us, in the previous example, that was numbers bigger than 1 and less than negative 1. Okay, so this is for a power series centered at 0, and then we just kind of generalize it in just a moment. But let's look at it more visually. So we're saying that our series converges between some numbers, okay, and it diverges beyond those numbers. Okay? And then this capital R, we're going to use that to represent what's called the radius of convergence. So now kind of expanding that theorem with this corollary, this is for a power series centered at somewhere we're calling A. Okay, so A could be 0 or maybe it's not 0. This is just generalizing our power series. So the convergence of a power series centered at A can be described by one of the three outcomes here. So the first possibility is that there's some positive number, we're calling it R, such that the series diverges when this x minus a quantity is bigger than R, but with absolute value, remember what that means. This also represents that this is less than negative R. So remember, anytime you're dealing with absolute value, you have two possibilities, where it's this same thing exactly as written, or the opposite with a negative sign. So let me just kind of write that so you don't have to kind of guess at what I'm saying. I'm saying that this also means x minus a is less than negative R. Sorry, it's for my scribbly writing here, but this says that this as well, okay? It diverges like basically outside of however big R is, but it converges absolutely for any values less than R, so between positive R and negative R. Again, referencing our last example, that was between negative 1 and 1. All right. Now, the series may or may not converge at the endpoints, and that's what we just kind of worked on. So it may or may not converge at the a minus R, so the center minus the radius, or a plus R, the center plus the radius. So for our example, we had to check, did it converge at 1 and negative 1? So that's one possibility. The other two possibilities are the following. The series converges absolutely everywhere for all x. Okay, so in that case, your radius of convergence would just be infinity. Okay, your series converges everywhere. The other possibility is that the series converges at only one value, only at the center right here, which would be 0, okay, right? If you think plugging in a here, a minus a is 0, and it diverges everywhere else, so it only converges at that one point. So your radius of convergence would be 0. All right, so notice you have three possibilities here, but in the very next slide, I'm going to show you how to break this down. Possibility 1 is the one you're going to see pretty often, and this possibility breaks down into 4 different cases. It looks like this. So 6 possible intervals of convergence. Don't let this overwhelm you. 4 of these are almost the same. Okay, the top 4, 1, 2, 3, 4, are pretty much identical other than the endpoints. So the only difference between the first one and the second one and the third one here are whether or not you can include the endpoints. The first one, you're including this left endpoint and the right endpoint. The second one here, you're only including the left endpoint. The third one, only the right endpoint. And then this fourth one, neither endpoint worked. So for our example, it was actually this third case, because we tried -1. It didn't work. Our series didn't converge for the left endpoint, -1, but it did converge for the right endpoint of 1. And then the other two possibilities is just that your series converges for all x numbers, so everywhere, and then it diverges, or the last possibility is that it diverges everywhere except for right at this one number. Okay. Now, how do you test a power series for convergence? So we're just going to break it into these 3 steps. Number 1, you use the ratio or root test, which we just did in our example, to find the largest open interval where the series converges absolutely. Okay, and so if it makes more sense, you can write it like this. They're saying that your x numbers are greater than some value and less than some value. Okay, and it's from your center. So if your center number, for example, let's just pick a number, let's say 4, then this just looks like 4 minus the radius of convergence, and then over here 4 plus the radius of convergence. Now, part 2, if R is finite, test for convergence or divergence at each endpoint. This is exactly what we just did. We used the alternating series test on the one endpoint, and we actually used the p-series for the other endpoint. And then last, for our interval here, for x minus a greater than r, but with absolute value, so it's basically back to this right here, this interval, the series diverges. I'm sorry, this is the greater than case, so it's the exact opposite of what I have up here. The series diverges outside of this interval, and this is because the nth term test. The nth term does not approach 0. Okay, so anywhere outside of what we call the radius of convergence, our series would diverge. All right, and that is our power series and how to test for convergence.